Hello everyone, I'm Ken Lee. This is the paper that I'm going to present today, and this work is collaborated with Zhifeng, Matt, Farhana, Hanan, and Timos. I guess the first question that you might have is, what are user-defined urban areas of interest? We implemented a system to demonstrate this based on real estate data in Melbourne. So on the left side of the screen, user can define a query, and the area that satisfies the user query will be shown on the map on the right side of the screen. For example, a user might be interested in all the regions in Melbourne that are within 15 minutes walking distance to the nearest train station. So they can also relax this query to 20 minutes or 25 minutes, and this is the result on the right side of the screen. Or they can add another criteria. For example, they want this region to also have a train time to the city center within 30 minutes or to 40 minutes. Or they can also have a completely fresh query. For example, if they are interested in all the regions in Melbourne with a property that are below $1 million. So an AOI is just an area that satisfies the user query. Normally, they could be represented either as a set of individual points or polygon-based regions. Our focus in this paper is how to generate those regions based on points, which is also known as footprint method. There are dozens of footprint algorithms proposed in the literature. One of the most popular methods is to construct a convex hull and then use a digging method to make the boundary more fit into the data. For example, here they find the largest boundary edge of the convex hull and then remove it to get another two edges as the new boundary to make the boundary more fit into the data. The only parameter here is when to stop this process. Unfortunately, this parameter could be very hard to define, and different parameters can give a different result. For example, here the two figures are generated based on the same method called AOI-shapes for the same query. On the left, a smaller threshold of chi gives a very complicated shape. On the right side, a larger threshold of chi means the boundary might be too large. Another issue of the literature is most existing methods cannot recognize multiple regions or detect holes. In our paper, we summarize 30 footprint methods as shown in the table, including the main construction process of each method and the characteristics of the generated boundary. So this boundary, the characteristics include whether they can detect holes, whether they can recognize outliers, whether they can recognize multiple regions, and whether they are being parameter-free, and whether they can support incremental method. So unfortunately, we summarize the method, we find out existing footprint method, they fail to support at least one of the following features. And our proposed AOI-shapes will be able to support all of those. The problem definition is simple. We separate the data points into two sets. Those satisfy the user query and those don't. And our objective is to compute the boundary of the region that are formed by the points that satisfy the user query, including the outliers. The general idea of the proposed method is also to divide the space into two parts, those that satisfy the user query and those don't. In the paper, we first propose the baseline method, AOI baseline. The method includes an offline pre-processing step and a query time pre-processing step. At the pre-processing part, we divide the whole space based on all data points by building a de-Lawley triangulation. At the query processing process, after user defines their query, we first get all the points that satisfy the user query, and then based on those kind of points, we find boundary edges, recognize multiple regions, and detect the inner holes. The most important step is to find the boundary. To do so, we divide points, edges, and regions into a few different types. So there are two types of regions, outside regions and inside regions. All those cannot shadow paths are inside regions, and at rest is outside regions. And the points, if it's in the outside regions, it's outside points, and if it's inside the inside regions, it's the inner points. We also have the boundary points, P2, P3, and P4. We also have some outlier points, which are the points that satisfy the user query but are in the outside region, and they are not connected with any other inner points. We also have dangling points, which are 2 points connecting each other but not connected with other regions. We also have outside edge, inside edge, boundary edge, and dangling edges. Based on those labels, the AOI baseline will be able to recognize multiple regions and detect inner holes. After that, we propose the AOI-shapes based on the doubly connected edge list data structure, also known as TiiS. TiiS links 3 sets of record: points, edges, and faces. Points are the same as in the AOI baseline. The edge here in TiiS is represented as 2 dots or 2 half edges. For example, P6, you have P6 to P5 or from P5 to P6. And you also have faces, for example here. In the baseline method, we need to find the boundary edges by traversing all the points and triangles. Since the TiiS structure links points and triangles, we only need to traverse the points that satisfy the query and then check the linked triangles. This makes it much efficient to find boundary edges. Also, in the baseline method, after defining the boundary edges, we'll start with one edge and then traverse all the edges in the boundary edge list in order to define a region. Since TiiS links points and edges, we can now easily find the adjacent edges and recognize the region. Since the edges in the TiiS structure have direction, the process for detecting inner holes are also much more efficient in AOI-shapes. Until now, the proposed AOI-shapes will return the same result as the baseline method. Unfortunately, they still have some issues. For example, on the left figure, there are regions connected via the C, which is not expected. Or on the right side, if there is no user query, the result will be the same as convex hole. To address the issue, we add a digging process in AOI-shapes to make the result shape more fit. We consider a boundary edge to be too long if the opposite angle of the edge is obtuse, and we continually to remove this one until there is no such cases. This digging process will be part of a step of finding boundary edges. In the paper, we also proposed 2 incremental methods which will update the algorithm from this step or from this step after user update their query. We conducted extensive experiments to test the effectiveness and efficiency of our method. We compared the baseline method and AOI-shapes with 6 state-of-the-art blueprint methods. We implemented an online demo system using Australian real estate data to demonstrate the proposed AOI-shapes for the use of interactive visualization of user-defined AOIs. Besides AOI-shapes, we also implement a few state-of-the-art alternatives for comparison. In the paper, we first report a few results of different methods based on the same query. The result that is most similar to our AOI-shapes is chi outlier. It is able to recognize outliers and multiple regions, but not able to detect holes. However, chi outliers takes 24 seconds to generate the result compared to 0.06 seconds in AOI-shapes for the same query. Since the boundary of AOI is usually vague and unknown, there is actually no ground truth of AOI for quantitative evaluation. However, to quantitatively compare our algorithms with existing methods, we conducted experiments by reconstructing footprints derived from known ground truth regions, such as city boundaries, and we created 4 datasets and reported the results in our paper. We also gave quantitative evaluation for the efficiency part of the AOI-shapes and the incremental methods in the paper. This is a summary of the contribution of this paper. Thanks for watching.